-70. The furthest from +65, -8. At what point during the action potential is the ECG for sodium at its weakest? +30. So, at what point during the action potential is sodium movement the fastest? So not the total amount of sodium that's moving across. It could be a little, it could be a lot, but the rate at which it moves across. Where is it going to be the fastest rate? Furthest away when you have the strongest ECG, right? That's the force pushing it through the membrane. Now, as far as how much can go through, depends how permeable the membrane is to that ion. But whether it's a little or a lot permeable, you know the sodium is going to fly through those channels at a high rate. Strong force. So that would mean that the sodium influx is progressively decreasing as the voltage goes up, right? As we are depolarizing, sodium influx is slowing down. At what point would it stop if we just kept the channels open indefinitely? If the inactivation gates didn't close for some reason? As far as you can go is +65, right? So it slows down until +65 and it stops. What if, though, we changed the voltage of the membrane to +100 and we open channels for sodium? Would it move at +100? It'll move at any value other than what? +65. As long as you're above or below +65, it's going to move. It only doesn't move at its equilibrium potential, at exactly +65. Which way would it move if the membrane was +100? It would start moving out. Why? What's changed at this point? Because the concentration gradient doesn't change, right? When you change the voltage, the electrical gradient changes. What's happening to it? It's now stronger than the concentration gradient, and it's directed in the opposite direction, right? When the membrane potential is positive, the electrical gradient for sodium is directed. Yeah, let's just do it over here. +100 millivolts. Concentration gradient for sodium. Greater, weaker, or the same? We just went from -70 to +100. It's the same, right? Voltage has no impact on concentration and vice versa. So the electrical gradient has changed. Is it still directed in? No. So when you map this out like this, you do want to account for the charges so you can see what's going on. So at +100, the inside is now positive. The outside is now negative. Sodium's positive. The inside's positive. It's repelling it. Outside's negative. Sodium's attracted to that. The electrical gradient is directed out. How long do I make the arrow? Shorter than the concentration arrow? Longer? The same? Longer. And then to figure out the ECG, you simply take the difference. It's directed out. And if we changed it to +150 millivolts, would it still go out? Would the ECG be stronger or weaker? Right? +200 and so on. It just, the further you get, the stronger the ECG. But if you go the other direction, +100, +90, +80, +70, you hit +65, there is none. And then you go below +65, which way does sodium start moving out? Starts moving in. Right, so +50, +40, +30, +20, right? All, they just, the further you get, the stronger it is. At what point during the action potential is potassium's ECG at its strongest? At what point during the action potential is the ECG for potassium the strongest? plus 30. And sure enough, when do we open channels for potassium? At about plus 30. Now, is it hitting plus 30 that causes the potassium channels to open? No. Threshold does, right? It's just a delayed response. And we said that the ECG is strongest for sodium when the membrane's really negative, right? And the most negative it is during the action potential is negative 80. But when do we actually open the channels for sodium? It's not at negative 80, it's at close to it, negative 70. But that's why there's a flooding of sodium across the membrane, because it is really negative, and so the ECG is really strong. And then we actually can quantify the increase in permeability too. How much of an increase when we open all those activation gates? Increases 1,000-fold compared to rest. Little permeable to sodium at rest, 1,000 times more permeable once we open those voltage-gated sodium channels. Why would it have to be a huge increase in permeability in order to depolarize the membrane? Not 10 times, 20 times, but 1,000 times more permeable. Why does it take something like that? Right, all those channels for potassium, and potassium's constantly leaving, and you have to overcome that. You have all this positive charge leaving, you have to bring enough positive charge in to overcome that and actually depolarize the membrane. Does that make sense? I'll probably ask the same question a few different ways as we keep going. You notice how I keep coming back to the same concepts again and again? The ones that show up on the exam?
I have a quick question. So at the hyperpolarization, the potassium, it's still open? Like
The voltage gated, right, on top of the lead.
And then the sodium also opens? No.
Are they still resetting at that point?
So at what point do the voltage gated sodium channels open? Yeah, I know a few before, a few after, but let's just simplify threshold, right? And then at what point on this graph are they closed? And no, they don't all close at once, but if you're going to point to a value, plus 30. So after plus 30, sodium movement's unchanged, right? When we're at plus 30 and we've closed the voltage-gated sodium channels, we're back to resting conditions for sodium. So everything else that happens is potassium. Potassium does the repole, potassium does hyperpole, sodium's out of the picture at this point. But the channels, something is happening to the sodium channels. And that's related to the next topic, refractory. After a short break.